To Pomodoro Joe for Sunday, January 15th, 2023. Today we'll be looking at LeetCode problem 2421, number of good paths. This is a hard problem. In fact, this is an extremely hard problem. I already tried solving this one using a depth first search algorithm, which did not run in the time given. So today's solution will be a union find solution that I did not come up with on my own. This one is something that I had to read about. So here's the problem description. There's a tree, a connected, undirected graph with no cycles, consisting of n nodes numbered from 0 to n-1 and exactly n-1 edges. So you have a tree, you're given a zero-indexed integer array, vals, of length n, where vals at I denotes the value of the ith node. So you have some list of values. You're given a 2D integer array edges, where edges at I is AB, which denotes there exists an undirected edge connecting nodes A and B. So we have a list of edges to define our tree. A good path is a simple path that satisfies the following conditions. The starting node and ending node must have the same value. So that's values in our vals array. All nodes between the starting node and the ending node have values less than or equal to the starting node. Return the number of distinct good paths. Note that a path and its reverse are counted as the same path. Okay, and also note a single node is considered a valid path. All right, we'll put 25 minutes on the Pomodoro timer and get started. First thing we'll do is convert these edges into something a little bit more usable. So we'll have a dictionary that maps the nodes to all of the connected nodes. So let's see, we'll have some result. Set it to 0. Actually, we know that for every node, each node is by itself a valid path. So we can have length of vals as our initial value for our result. And we will return our result at the end. Now we'll create our default dictionary of nodes. And this will be a set. So we'll have a mapping from a node to the set of connected nodes. And for A and B in edges, we will say nodes at A, we'll add B. And for nodes B, we will add A. Now we have all our connected nodes. Next thing we'll do, we'll be grouping these nodes by value. So we'll need some mapping for nodes by value. And that's just going to be, again, a default dictionary. Or in this case, we'll just make it a dictionary. Okay, so then we want to say we're going to go through our list of values here for I in range of the length of our values. The nodes by value. At vals. So at our current value, we'll add this value. So in fact, we do want a default dictionary. And that'll be also a set. So this is a mapping of value to a set of nodes that have that same value. So for every value in our list of vals, we will set the value as the key and a set of nodes as the value for that dictionary. Okay. Now we need to define our union find functions. So in this case, I'm actually not going to call them union find. I'm going to call them something else. I'm going to call them group. So we'll have some we'll group nodes. This is equivalent to union. So we'll have node 0 and node 1. For now, I'll just pass. And then we'll have some find group. So this is equivalent to the find for the node. And again, I'm just going to pass for the time being. So what do we need for our union find? We need some data structure. So we'll call it UF for union find. Or actually, I'm just going to call it groups. So these are going to be our groups. And we have some dictionary that maps a node to a node that represents that group. All right, so in our group, when we group two nodes together, we basically are just going to say, okay, groups for node 1 maps to whatever group is for node 0 or vice versa. So in this case, we need to find the group. So we'll find the group for node 1 and we'll set the group for, it's actually, we need to find the group for node 0. And I already say I have a typo. This is a function. So we'll find the group for node 1 and we will map the group for node 0 to the same group as node 1. So now they share the same group. We're putting them into the same group together. All right, how do we find our group? Well, let's see. If n is in our groups, then we can actually, let's say if n is not in our groups, then we need some default. So for groups at n, we're just going to set this node as being the representative for its own group. All right, now if groups at n, so if this group, let's see, if this node does not equal, so if this node is not the representative node for this group, well then we want to find what is the representative node for this group. So we will do a recursive call to find group on groups n. So we recursively call this to find, well, what is the representative node for this group? And then we want to set this group n equal to that representative node. And then we will return our group n. I'm not explaining this very well right now. I suggest if you look up union find, this will be, I think, the standard algorithm. It's a little bit tricky to explain. So this should give us our union find algorithm. Now what's next? Oh man, we are running low on time. Okay, now we need to go through every node in our group, in our tree, but we want to go through them by value because we want to build up our groups from the smaller values up to the larger values. That way we know any node within our group has a way to traverse to any other node in the group because there are no nodes of larger values that would be blocking that path. So let's see, let's get our list of values here. So our list of values, well, that's going to be, let's see, we have some nodes by value. So the values are just the keys to this nodes by value. But we want to do this in a sorted order. We want to go from the smallest node values to the highest values. So we're going to sort that. All right. Now for our value in our values. So we're going to go from the smallest value to the largest value, and we're going to get all the nodes. So in fact, we can just say for every node in our nodes by value for this value. So for every node that has this same value, we're going to go through and group all of its nodes, all its connected nodes with this node. So for connected node in our nodes for this node, so remember our nodes is just our list or our set of connected nodes. So for every connected node in our list or set of connected nodes to this node, we are going to say if the value of that connected node is greater than the value that we're currently looking for, we're just going to continue. We're not going to bother doing, we can't go to this node. If this value if the value for this connected node is less than or equal to our current value, well, then we're going to group these nodes together. So we're going to call our group nodes. And we'll pass in our node, and we'll pass in the connected node. So we're building up a group of nodes that are connected that only have values less than or equal to our current value. So that means that any node in this group is traversable. Now we just need to find out, well, how many nodes in these groups have the values that we're looking for our endpoints. So we'll just say count nodes of val in groups. Okay, so we need to figure out how many groups we have. So let's see, what do we call this? We called this guy group, so we don't want to shadow that with some, let's see, we'll just call this like groups by value. Okay. So now for our node, for every node in our nodes by value, so these are all the nodes with the value we're looking for. We'll find that node's group. What group is this node in? We can do that by saying find group on that node. And we'll say groups by value for this group. Well, we're trying to count how many nodes have this value in this group. So we're going to say plus equals 1, which means that we need to make this one a default dictionary with int as its default type. So now we're counting out how many nodes of this value exist in this group. And now finally, we need to go for every group. For, let's see, we call this node group. I can just call this group, I think, for group in groups by value. Now we can say for every group, how many nodes, we've counted how many nodes have this value. We can do some combination of traversals to every node. So this is going to be, whoops, shoot, there we go. So our result will increase by some combination of all the groups. So let me just copy this. Running super low on time. I think I'm actually over time. Groups by value for this group. And we want to choose any two nodes of that value and then add that path to our result. Oh man, I think this should do it. And I have a typo. Finally, we've got all the typos taken care of and we can submit. And it passes. Once again, I cannot take credit for solving this one on my own. I definitely did research into this one. The depth first search algorithm seems more intuitive, but it definitely does not run in the time limit given. So this algorithm does all right. It's 80% better than the other algorithms in terms of submissions for runtime, and it beats 52% in terms of memory. And I definitely was not being super clean with my implementation, so I'm sure there are ways you can improve upon this. All right, that's it. We're totally out of time. Hope you enjoyed this. Hope you had fun. Write better code.